Okay, stoichiometry part 3. We're going to talk about hot dogs. Alright, so if you buy 4 packages of hot dog buns rather, and there are 8 of them in a package, and you buy 5 packages of hot dogs, and there's 6 of those per package, and you have to have 1 hot dog plus 1 hot dog bun to make a complete hot dog meal, how many hot dog meals can you actually make? Well, if you do the math there, you can make 30. You have 30 hot dogs, and then you run out. So you even have 32 buns, you can't make a full hot dog meal without that hot dog. That causes a problem. So you run out of something first. Technically, companies do this on purpose, but it also applies to chemistry. So if we have a balanced chemical equations, just like that simple hot dog recipe, if we have 2 sodiums required plus 1 chlorine molecule goes to 2 sodium chloride. So how much sodium chloride we can make will depend on which of those reactants, sodium or chlorine, runs out first. And we call the thing that, we call those the limiting reactant or limiting reagent. Whichever reagent or reactant, they're the 2 words for the same thing. That thing determines or tells you how much of your product you can actually make. Once it's gone, you can't make any more. Right? Once you run out of sodium, you can't make sodium chloride. Or once chlorine is gone, you can't make NaCl. It's hard to do it without any Cl. That's why it's the limiting reagent or reactant. The other one, the one that you have lots of, extra of, is called your excess reagent or excess reactant. So it's the one that you've got extra, surplus, a lot of in the reaction. So if we go back again for a second, if we only had a little bit of sodium and it runs out, if we have a lot of chlorine, there'd be extra chlorine and excess, more than we need. Ideally, you want to have an even amount of both. That's not always the case when you're doing a reaction. Alright, so let's look at this with an actual problem. So if you have 54 grams of sodium and 60 grams of chlorine, which is your limiting reactant? Now, let me tell you straight up, people often do this wrong and they go, oh, this number is lower. That must be my limiting reactant. Not necessarily. You cannot tell from the grams which one's your limiting reactant. You have to go through a bunch of steps to find it out first. So don't just go guessing based on whatever's lower to start with. That may or may not be your final answer. You need the work to go with it. So how we solve this is by determining how much of our product each of those reactants could make if we used all of it up. So we're going to take our sodium first. I got 54 grams of sodium, and I cancel my grams and go to moles of sodium. That's partway there. That's not my product yet. So I then have to cancel my moles of sodium and go into moles of my product. Again, mole ratio, 2 and 2 in this case. I can change the of what, because these are both moles. Now I'll go one last step to get to amount of product, so grams of my product. So from moles to mass, I use that molar mass, grams per mole, which we find again from the masses of sodium and chlorine on the periodic table. So if we use all the sodium, we do the math, we'd be able to make 137 grams about of sodium chloride, of salt, of our product. Okay, that's dandy. But how much could we make if all of our 60 grams of chlorine was used up? Well, we need to find that out next. So we're going to do the same thing, and some of this will look awfully similar. So the same thing, but now with chlorine. So we're going to start with our 60 grams of chlorine. Again, we do the molar mass of chlorine here into moles, molar mass, grams per mole. This is the mass of 2 chlorines. Once we're in moles of chlorine, we need to get from moles of chlorine to moles of our product. So moles of chlorine here, we go into moles of sodium chloride. Since they're both moles, a mole ratio, a mole sandwich if you will, we can change the of what's. Now it's a 2 to 1 mole ratio here compared to a 2 to 2 ratio here because there's only 1 mole of chlorine up here. But again, we need the amount, so the of what to our products. So we go from moles to grams of sodium chloride. This last step should look awfully similar because, hey, we did it exactly the same for the first one. Now we're in grams of our product, so we're done. We do the math and we solve and we get 98.91 grams of sodium chloride. Okay, we have two answers, but only one of them actually gives us what we need. So let's think this through. If all of our sodium was used, we could have made 137 grams of sodium chloride. If all of our chlorine was used, we could have made 98.91 grams of sodium chloride. So this amount is less, right? So once our chlorine is used up, once we've made 98.91 grams of our product, sodium chloride, all of our chlorine is gone. Once it's gone, is it possible to make more? Is it possibly up to 137 grams if after 98 grams all of the chlorine is gone? You can't. You have no chlorine left after 98.91 grams, so there's no way to get this much product because all of your chlorine is gone. So if this one runs out, this one's lower runs out, that means chlorine must be your limiting reactant or limiting reagent. That's what we're looking for. Yeah, that's what I just explained in words. Okay. So that was an example of that. Make sure you took notes on it. Another piece we need to talk about is percent yield, which you guys have done things similar to this before, so hopefully it's not much of a stretch. Percent yield is just the actual yield, how much you actually got, you yielded, you produced, divided by what in theory you should have gotten. So like if you're in a lab and you should have made 112 grams of the product, but things went wrong, no one's perfect, so you made 102 grams. You put 102 actual over here on top, divide by 112 grams you should have gotten, and multiply by 100 to get your percent yield. Something on the 90% there. Alright, so let's try one. If you should be able to produce 48 grams of calcium sulfite, but only managed to make 36 grams of calcium sulfite, what would be your percent yield? If you think this makes sense, it's easy, go for it. Go ahead and hit pause and come back. If not, I'll walk you through it. Well, if you should have been able to, that's in theory you should be able to make 48 grams, so that'll be your theoretical yield. But you managed to make this much, that's what you actually made, produced. So that would be your 36 grams on top. You take 36 grams divided by 48 grams, multiplied by 100, we get exactly 75% yield. You yielded, you produced 75% of what should have happened, should have been able to get. That's about as straightforward as it gets. Okay, see if you can do these. So you've got an example problem. Try and look at that one, pause and do this one before I show you how it works. This is back to the limiting reactant one. Kind of. Okay, here we go. So we know we've got 60 grams of aluminum and 40 grams of oxygen. We're saying how much of our product, right here, Al2O3, can you produce? Well, we got to go through and solve for each one, because we might run out of aluminum first, or we might run out of oxygen first, and we don't know until we solve for the actual product. So 60 grams of aluminum, grams of aluminum must cancel, go to moles of aluminum. That's the molar mass of aluminum. We don't want moles of aluminum, so it'll cancel, go into moles of our product, and a mole ratio, mole and mole, so we can change our of what. Those numbers come from the balanced equation. We don't want moles of aluminum oxide, we want grams of it. So one last step to get from moles to grams using aluminum oxide's molar mass, adding up 2 aluminums and 3 oxygens. Then we do our math, and we get 113.37 grams. Is that our answer? Maybe, but we don't know because we have to do the other part, which is doing the 40 grams of oxygen. Same idea. We'll do this one a little bit faster. 40 grams of oxygen, cancel grams, go to moles. It's 32 because it's O2. So 32 grams into 1 mole. Mole ratio, there's 3 O2s for every 2 aluminum oxides. Now see, this is where people get confused. If you don't put the full mole of what? Mole of O2, mole of aluminum oxide, people don't know what needs to go next, what cancels, and they get really lost, especially when we keep going forward. So please add all those for your sake and for mine. I'm going to make you show it, but it's going to make your life much easier if you actually write it down. Last step, moles of aluminum oxide to grams of aluminum oxide. Again, this step should look the same. Our answer comes out to 84.97 grams of Al2O3. So we can't make both of these. One of them is going to run out first. This number is lower because after 40 grams, you can only make this much. That means all the oxygen's gone, so you can actually only make 84.97 grams of aluminum oxide. This much would only work if you had more oxygen, but we run out. So the answer would be 84.97 grams of aluminum oxide. It's kind of impossible to make Al2O3 without any more O. Oh, yeah. Alright, whoops. And if in that same problem, if you ended up with 72 grams of Al2O3 in the lab, what would your percent yield be? Alright, well we know that we actually got 72 grams here. And we know we should have gotten 84.9497. Pick one, I don't know why those are different. They shouldn't be. About 84.95-ish grams of Al2O3. We need to take our actual over our theoretical times 100. Should get something by around 84.7%. If you don't, look back. What do you know? Alright, another one. What's your theoretical yield for chlorine if you have 36 grams of lithium chloride and excess bromine? Here, they tell us what our excess thing is. So we don't have to do this twice, just once, because we know that bromine is in excess. So we can skip this one, it's in excess. We can just work with our lithium chloride amount, which they gave us as 36 grams. And then on the theoretical yield, which is how much in theory you can make when you solve it, for chlorine. So we're going to start with what we're given, 36 grams of lithium chloride, and turn that from grams to moles using its molar mass, lithium plus chlorine. Go from moles of lithium chloride to moles of chlorine gas using its mole ratio. So there's 2 moles of lithium chloride. Oh, didn't balance it yet here. There's obviously a 2 here and a 1 here. My pen doesn't work. But if you balance it, you should get 2, 1, 2, 1 as the balancing numbers. The last step is going from moles of chlorine to grams of chlorine, but it's chlorine's diatomic, so 2 chlorines. Do the math, and we get 30.11 grams of chlorine. That is your theoretical yield, because that's perfect. It's just the math. It's the stoichiometry that gets you to it. And there's some words to go with it. Oh, my head keeps moving around. There we go. Once you read that, you can pause or hit play when you're ready. Okay, so if you actually had 24.05 grams of chlorine, what would your percent yield be? Oh, it shows up too early. Just takes the actual amount, the 24.05 grams, divided by the theoretical we just found, the 30.11, times 100, you get 79.87% as your percent yield. So, about 80%. Not bad, but we'd like to get a 20% of product ideally. Right, here's one last one. It's going to go really fast. So here's the question. Pause it, give it a shot, then come back to see how it works out. Limiting reactant, if you have 46 grams of lithium chloride and 68 of bromine. So now you got both of them. So we just go through and solve both of them. So when both go to the same product, you can pick either one. So I'm going to go and choose chlorine gas, because we've already done chlorine, so I know most of those numbers. So similar steps, but just a different starting amount. Do the same thing with bromine. I move my head. Now, here I've got my bromine came out to a lower amount, which means bromine runs out first, even though it starts with a higher amount. So see how sometimes that number is the limiting reactant? So bromine, oops, is your limiting reactant.